Alright, this is our third and final video for section 1.6, working with our functions and our transformations. What we're going to do is finish it up with some dilations, where we're going to do some vertical and horizontal stretches as well as shrinks. So we've already spent time with our translations and our reflections. This is the only one that we have left. Alright, so taking a look at this U shape that I have here, I have some different options that I can do as far as dilations go. We can stretch this vertically, we can stretch it horizontally. What do I mean by vertically stretching it? So I just got to kind of get this. Alright, so here's where I'm starting. Stretching it vertically would elongate it, and it's just going to pull the graph down, and that would be a vertical stretch. So here's my, and then I'm just stretching it. I'm making it bigger by pulling it down. Also by pulling it up as well. Other option, if this is where I started, I could do a horizontal stretch, which a horizontal stretch is going to make it wider. So notice that a vertical stretch makes it taller and skinnier, where a horizontal stretch makes it, kind of shorter and fatter with this. That's one option. The other option would be to compress something. So you could do a horizontal compression, which is going to make it skinnier. You could do a vertical compression, which is going to make it wider. So the one thing you got to understand here is notice that doing a vertical compression can have the same type of outcome as a horizontal stretch. So a vertical compression is going to make it wider, as well as a horizontal stretch will make it wider. Same thing with a vertical stretch, could be ultimately the same thing as a horizontal compression. You can still get that same feel with this. All right, so start out with a function that we all know, with our linear function of y equals mx. If I was to, let's say, do a vertical stretch, I would end up with a graph that looks like this red one right here. This black line that I have here, we know that if it's y equals, I should say x, if it's y equals x, the parent function, we know it goes through the y-intercept of 0 and it has a slope of 1. Well, by stretching this, what it's doing here is it's still going through our y-intercept at 0, but our slope is going to be changing. And by making this a stretch, our slope is going to get steeper. So here we can say this is a slope of 1. It looks like approximately here we have a slope of 3. It looks like I'm going up 3 and over 1. So with a vertical stretch here, we'll notice that we would have we'd have a steeper slope, and that line of that function then would be y is equal to 3x plus 0. So a vertical stretch including that. Now if I was to do, say, like a horizontal stretch or a vertical compression, I would end up with something like this. Here, this looks like our slope is about 1/3. And so we would get something like y equals 1/3 x. So what the vertical stretches and compressions are going to do is it's going to change the rate of all of this. So let's take a look at the graph scale change theorem. So horizontal stretches and shrinks. We're going to start with the horizontal ones, and then we'll talk about the vertical ones. This whole chapter we've been talking about inside change versus outside change, and I'm going to continue with that idea here. When you do a horizontal stretch or shrink, that's our inside change. And the whole chapter as well, we've been talking about how whenever we do inside change, it's almost like it's the opposite of what we are doing. So when we are graphing a function, when we want to move it to the right 4 units, we have x minus 4. So we have to be real careful with that. Same thing's going to happen here. Here, when you have a horizontal stretch, we have the function of y is equal to f of x divided by c, or 1 over c times x. And it's this value of c right here, which is going to be telling us what our factor is and what we're stretching it by. A horizontal stretch takes place if the value of c is greater than 1. We do a stretch. Now you have to be careful with that, because when you look into the function then, It's not going to look like a number greater than 1. For example, if we want to say that c is 2, if I put a 2 in for here, I get f of x divided by 2. Or we could look at this being as f of 1/2 times c. If I want to stretch this by a factor of 2, when I put it into my function, it's actually going to be looking like I'm taking 1/2 of something, which actually we're stretching it. If we wanted to shrink something by a factor of c, we'd want that value of c to be less than 1. So here we could put in something like 1/2. So f of x divided by 1/2, realize that's when you divide by a fraction, you multiply by the reciprocal, so you get f of 2x. Same thing would happen over on the other side here. 1 divided by 1/2 would give us 2, and then we'd have 2x. So to kind of give you an idea here, here's some different examples. These are all dealing with inside change. We're taking our function, we're doing something to the value of x inside there. F of x divided by 2. People automatically think, oh, the factor is 1/2, so we're going to be doing a shrink. When actually this is going to be a horizontal stretch by a factor of 2. And the reason that it's 2, we're taking x divided by c. We're taking x divided by 2. Your value of c here is 2, making this being for a horizontal stretch. On the next one here, f of 2x. So people, again, once they sit there and say, oh, it's greater than 1, so therefore you're stretching it, which actually here we're doing the opposite of it because we're going to be shrinking versus going to be a horizontal shrink. And it's going to be by a factor of 1/2. Think about this right here. If this 2x right here, 2x would need to equal 1 over cx if you're trying to figure out what that value of c is. If I were to go ahead and divide both sides by x, that would cancel out the x's here, leaving me with 2 is equal with 1 over c. I could multiply both sides by c to get that out of the denominator. And then I end up with 2c equals 1, which then I would have to divide by 2. And here I would see that c is equal to 1/2. So our inside change here is looking like we are stretching it, but actually we're shrinking it. Next one here, 1/3 x. This would be an example of a horizontal stretch. Oops, I forgot that. Sorry, I forgot T up here. Stretch by, in this case, we would have it by 3. So I'm going to go and take a quick look at a couple examples for different functions. So let's take f of x is equal to, and we'll go 4x squared. So what we have going on here is we have something dealing with the inside change of the 4x. My parent function, I'm just going to draw that one in black. We'll say that's our parent, and we're just going to sketch out what this new function is going to look like. This 4x here, that 4 is greater than 1. However, it's not in the form of x over c. If we were to think about this 4x here, 4x equaling 1 over cx. Okay, once again, I could divide by x's here, and we could get that 4 is equal to 1 over c. Multiply both sides by c, so 4c is equal to 1. And we'd solve it here, and we get c is equal to 1/4. Because it's inside, that means that we're working with a horizontal stretch or shrink. So here, if I have a horizontal shrink of 1/4, that means it's going to bring our parabola and it's going to make it smaller. Another way to kind of help show this is with dealing with absolute value. So let's take a look at, we'll take h of x is equal to let's go 1/4 x. So the absolute value. Here's our parent function. 1/4 x. What this is going to tell us here is that we would be doing a horizontal stretch by 4. So a horizontal stretch is going to make it go out this way. Now, how I know that it's going this way, or another way to think about this, is when you think about absolute value, this is actually giving you two functions. It's giving you y is equal to 1/4 x, as well as y is equal to negative 1/4 x. That's where this graph comes from. And if you think about what is that 1/4 and that negative 1/4, well, those are your slopes. Of your parent function, you have a slope of +1, and you have a slope of -1 on the two branches of your absolute value. Here, what's happening with that 1/4 is that is now telling you what your new slope is. And the slope of 1/4 is going to be less steep than having a slope of 1. And here my slope would be -1/4. So that's another way to kind of help you think about it. A lot of these here, as far as we're just kind of trying to sketch them out just to get an idea of what they look like. Let's do one more. We could do the square root. So we could do f of x is equal to the square root of x divided by 5. So here's my parent function. X divided by 5 here, I'm going to think the opposite, so I'm not going to use 1/5, I'm going to be actually using 5, and so this here is going to be a horizontal stretch by a factor of 5, so it's going to get a little bit shorter and wider. Alright, so now what about vertical stretches and shrinks? Well, vertical stretches and shrinks are going to be the outside change taking place. If C is greater than 1, we will do a vertical stretch. If C is less than 1, and I should say also greater than 0, we're going to be working with a vertical shrink. So to kind of look at some examples right here, notice that all of these values here are outside of your function. It's not taking place inside the function, it's all outside. 2 times the function f of x, this is going to tell us that we're going to do a vertical stretch by a factor of 2. Here being 1/2, we would do a vertical shrink by a factor of 1/2. And then this last one, just be real careful, because we're not going to do a vertical stretch by 3. This one is also going to be a vertical shrink by 1/3. So just to kind of look at a couple examples real quick. Say let's do our quadratic here. So f of x is equal to, we'll do an outside change, so 3x squared. So that 3 is telling me that since it's outside, that's going to be vertical. And it being greater than 1, we would be doing a vertical stretch. And our vertical stretch would be making it a little skinnier here. We could do the same thing with dealing with absolute value. So we could take f of x is equal to, we'll go 1/3 times the absolute value of x. Here's our parent function, and 1/3 is going to do a vertical shrink, which is actually going to make this wider. And that 1/3 right there is also, once again, going to be looking at what the slope of your two sections here are. We're going to have a slope of +1/3 as well as a slope of -1/3. All right, so now to try and look at, well, how do you write these out? So here I have the natural log function, and we want to do a horizontal stretch of 3. Horizontal stretch is going to be inside, and we have to think opposite. So here we would be looking at f of x is equal to the natural log of 1/3 x, or x divided by 3. A vertical shrink of 2/3. Vertical is going to be dealing with outside change. So that's going to take g of x here, and we're going to keep it as our 2/3, and then we have 2/3 x squared. And a horizontal shrink is going to be inside. So w of x here, and that's going to end up giving us e to the power of x. Now, how you want to deal with fractions, many of you are going to know that it's really going to be the reciprocal, or we can do here x divided by 3/4, which when you divide by a fraction, we multiply by the reciprocal, so that'd be e to the power of 4x over 3. Just the same thing, like here you had 3, well now here it's 1 over 3. 1 over 3/4 is going to end up giving us 4/3. Alright, so there we have everything. I just want to take a look at, something with all the combined transformations and see if we can kind of identify what's happening to this function of k of x here. There's a lot of stuff going on. There's some inside change happening. There's some outside change happening. This stuff right here is all inside. And then the 4 is the only part that's our outside change. So to identify what's happening, first of all, that x plus 7 says that we are shifting our graph to the left 7 units. The plus 4 that's on the outside tells us we're going to move our graph up 4 units. And then you have this -2 that's over here. Well, this -2 is telling you two different things. First of all, it's telling you that we are going to reflect over the y-axis. And then the 2 right there, since that is inside, is telling us that we have a horizontal, and this is not going to be a stretch, it's going to be a horizontal shrink, and we'll be looking at by a factor of 1/2. So we have multiple things going on here. So now as you start to practice some of these combined information, make sure that you're jotting down any notes and let me know if you have any questions.